we're going to be talking specifically about gravitational potential energy and kinetic energy. Okay? So we use a bowling ball that will have a lot of potential energy because it's very massive and a lot of kinetic energy to show you how that goes and how energy is conserved. So I got this bowling ball here, it's pretty heavy, and right at this instant I'm holding it, it's not moving anywhere, it's not going anywhere. Therefore, velocity is zero, speed is zero, kinetic energy is zero. Right? Does this ball have gravitational potential energy? Oh yes, it does, a lot. It's pretty heavy, it wants to fall, and as soon as I let it go, it's going to fall. So it has gravitational potential energy. And at this instant, it has no kinetic energy because it's at rest. So now it has kinetic energy. So let me represent what's happening here at this specific point that I was showing you. Okay. At that point, all that ball had was potential energy. And I'm going to use yellow to represent my potential energy. Okay. It had no kinetic energy, therefore I'm not drawing it here at this point. Now, let's move it here to the middle. The ball is moving, right? So right here, at the lowest point, does it have gravitational potential energy? At the very lowest point? Yes, it does. It's not going lower because it's being held by the string, but yes, it does have gravitational potential energy. Still, it would like to fall even more. So let's draw the energy diagram at this instant, right here at the closest approach to the floor. Right? Does it have potential energy? Yes, it will have potential energy. Less than it had before, because it's closer to the center of the Earth. But it still does have gravitational potential energy. And now, does it have kinetic energy? Oh yes, it does. It actually has the maximum amount of kinetic energy it will ever have because it's at the minimum of potential energy. So it has kinetic energy. Green was a poor choice, given that it looks so much like the yellow. Huh? But if you add them up, the total should be the same. Okay? A little bit of potential, a lot of kinetic. When it goes right here at the very extreme, at the other side, again, all it has at this point, the maximum distance from the floor, is gravitational potential energy. And at that point, the velocity is zero. It has no kinetic energy. So it goes back to what we had before, right? So kinetic energy goes to zero, and then I'm back at the same amount of energy that we had before. So the energy is conserved. The potential energy is not conserved, the kinetic energy is not conserved, but the total energy of this ball is conserved. Approximately, right? Because if we wait too long, there's friction, and the ball is actually losing some energy due to the interaction with air and with friction. Now, the amount of energy at the end, there's no way it's ever going to be larger than the amount of energy that I had in the beginning. Right? Otherwise, I would be adding. Would be adding energy to this ball. We wouldn't know where it would be coming from. So I trust so much conservation of energy that I'm going to put my life in risk and show you how there's no way this ball can gain potential energy and come and hit me. So I'm going to use the stairs here just to make sure I don't move anywhere. I don't go anywhere, I don't cheat on you. Put it right here on my chin. Okay? And I'll let go. And I will not move. I will not bulge. And the ball will not hit and break my nose. Okay? I get the wind. It's a little bit windy. Now, in fact, it doesn't even come all the way through my face as it should if we had complete conservation of energy, right? But it's a pretty good approximation. It gets very close to my face. And the reason, again, why it doesn't get right back to the exact point where it was is because there's some loss of energy due to friction.